All right. So, hello, everybody. My name is Alan Pendon, and I am the Digital Demand Generation Manager at Electro. I'm excited to present this webinar with VIAVI Solutions on resolving PIM high RTWP issues via RF-Over-CPRI analysis. This session will be recorded, and links to the recording, as well as the presentation, will be sent to everyone after the event. Now, today's speaker is Dan Smedja, Domain Sales Expert, CIVT Wireless Metro Fiber from VIAVI Solutions. Dan has worked in the wireless industry for 26 years. He began his wireless industry career as an RF applications engineer. And as part of VIAVI Solutions, he is currently a domain sales expert for fiber, Ethernet, and RF, 5G and R, LTE, interference hunting, and PIM testing. Dan plays an integral role in VIAVI for helping to determine the testing solutions for cell site 4G/5G, map creation, and provider acceptance. Now, just a little bit about Electro. We are the largest testing and technology services provider. We have over $1.1 billion in inventory, which means we have a lot of selections for your needs. Electro has invested more than $100 million for new inventory. We have over 122,000 solutions in stock, 27 offices and inventory centers that can deliver to over 100 countries, and over 600 specialists to help you. Now with that, let's get started with the webinar. Hey, Dan, how are you?
Good. Oh, I'm unmuted. Good morning. Wanted to start my video to give everyone the before picture, which you show on your slide, versus the reality of more than 26 years now. So it's an old picture. Am I able to share my screen when you're ready? There you go.
I am giving you control. And here we go.
All right. First of all, good morning, everyone. Thanks for joining us here with the Electro. Again, I'm Dan from VIAVI. With me is TJ Ford. He is my partner in crime here. So you'll hear him pipe up every once in a while. We have about an hour to talk about PIM mitigation, RTWP, interference based on testing at the fiber versus traditional PIM testing, which is done, with a Rosenberg or a Kalis two-tone PIM tester. So we have an hour just to chat about it. So let's jump right in. We're gonna gloss over what is PIM. We're all here for the same reason. It's what we're focusing on as near field interference. It's a big problem in the industry, and we're gonna talk a little bit about how do we use the fiber interface and the packetized RF to do testing in a different way. Some of the differences between traditional PIM testing and the way that service providers are doing it now. And then we're going to go right into the examples and a question and answer session, right? So we'll jump right in. What is PIM, right? What is passive intermod? The reality is it's the mixing of multiple signals, traditionally 2 fundamental signals when we're doing it with a test set. But in the real world, you take any 2 provider signals. We can focus in on AT&T or T-Mobile or whoever. I'll probably spend a lot of time using AT&T examples because they have kind of the worst of the worst, not because they're a bad company, but the frequencies that they were allocated. As these signals mixed, they create intermodulations, which fall in very predictable patterns. And unfortunately for us today, those patterns, they tend to fall right in the uplink of that same transmitter or same antenna or same tower or rooftop, whatever you want to say, which causes a high noise floor. In other words, RTWP, total wideband receive power, right? Receive total wideband power. I always get that one backwards. And that, of course, affects the distance your site can travel. It affects how many phones you can get onto the system. It affects the quality every time a new phone enters in and the quality of all the existing users out there, and it decreases their revenue. So that's why we're here. And it is becoming a much larger problem over the last 2 years. So what is it in a real world example? This is an AT&T example, to be very clear, because their frequencies that they were allocated happen to be the worst case scenario, but it's not limited to AT&T. This covers T-Mobile, this covers Verizon. If there's anyone covering US Cellular, it would cover them too, in varying degrees of severity. So what happens in an interference environment, in a self-made interference environment, PIM, you're going to have two transmits from said LTE provider. Could be 5G, but predominantly it's LTE right now. So in this example, the purple square on the left is band 17, which AT&T's traditional 700 megahertz downlink, so transmission. And then AT&T also won the FirstNet public safety band, which is band 14, also in the 700 megahertz. It just so happens that the space between those two, one at 739 megahertz, one at 763 megahertz, that space, when those two mix together, they will create a third order intermodulation and a fifth order intermodulation that fall directly in the uplink of those exact systems. So your band 17 uplink on the far left of your slide centers around 709 megahertz. That would be the phone's transmit or the base station's uplink. As it sits there, and if you look on the right side, you have band 14, the exact same problem, the phone's transmit or the base station's uplink. Those two fall in the perfectly wrong spot where the two purple transmitters hit something, and they create a massive problem. So what happens is you could go to any tower that has AT&T on it, or any T-Mobile tower that also has AT&T on it, and we'll get to a T-Mobile example here in a minute, where it doesn't involve AT&T. It raises. And so we have to get out there, or the service provider will end up hiring contractors, PIM crews, whatever, to get out there and try to mitigate and fix this and look at a cost analysis to figure out, is this something we can fix versus what it's costing us from our customers. Hopefully that makes sense. It is fairly complicated, but hopefully the slide comes up and makes a little bit of sense on it. By the way, there is a chat window open, which I forgot to mention up front. If there are any questions moving along, by all means, put them in the chat window. I'll try to answer them in as real time as I can, and we'll have a 5 or 10 minute question and answer session at the end as well. So this is a quick example of what PIM looks like with some numbers. T-Mobile example, I realize it's not in the slide deck as I look at my next slide, but they have the same problem with their 600 megahertz, their 5G/LTE band at 600 megahertz, mixing with 700 from themselves, because they do own a signal right around 731 megahertz. And those frequencies fall in not only their bands, but they fall in the Verizon band. They also fall up in the PCS and AWS bands. A little bit less severity, but again, it's still a problem and it still needs to be looked at. So we have a very large problem in AT&T. We have a large problem in T-Mobile, and it's all based on the frequencies that they were allocated and they were given, or purchased from the FCC, as well as co-location. You can put a T-Mobile and an AT&T site at the same place. They will mix together. So there's no reason you can't mix multi-companies around. So. A quick look and a preview of what we're going to talk about later on the tool itself, and this is the screens from our analyzer. Since we're not dealing with fundamental CW tones that people who've done PIM testing in the past, we're dealing with carrier grade signals. The signals will look different, and we call that a slope in most cases when we're dealing with low band. And so this is an example, and I'll have various examples of what this looks like at the rest of this presentation of what a bad PIM looks like in the uplink or in the phone's transmit band as seen by the base station. On the left side, you have the traditional band 17, 700 megahertz AT&T. On the right side, you have their public safety or FirstNet band 14. And again, these in this example were created because they're both transmitting. And when that happens, based on the little picture we put at the bottom, you get these third order intermodulations that are happening. And they create a slope in the signal. And actually the whole noise floor has risen up high enough, the base station can't even see the transmits from any mobile out there. It is effectively killing the base station from any type of service. So it can transmit, but it can't receive any of the calls because the noise floor is too high. And so just for a little bit more education, then we'll jump into the toys. What does that mean? It means when the base station can't hear a phone, it tells the phone to transmit higher power. So the phone starts to transmit higher power, and the base station starts to transmit higher power to get to the phones because it can't see the phones. So you end up incrementally increasing the power not only on the downlink, but on the uplink. Not only does that create a problem, you're killing your batteries of your phone, the phones are having to transmit higher, but as the phones transmit higher, they create interference on other cell sites that are in the vicinity, right? So it's not just a one for one, it's a one for many. So when we talk about PIM as a problem, it is a massive problem for carriers out there. So, all right, let's jump into that. I think we've had enough education on that. CPRI. So what is CPRI? CPRI is a technology that runs over fiber between the radio unit, either on the top of the tower, on top of the rooftop, and the baseband unit at the bottom, which is a controlling device. The good news is when we deal with CPRI, it's exclusively done for LTE, almost 100% now. There's very little LTE out there that won't be CPRI, which is good. And a lot of the low band 5G, so the 600 megahertz TMO, the 850 T-Mobile, 850, early this morning, Verizon and AT&T is all based on this backhaul technology or this front haul technology. Why we like it is the radio on the tower on the rooftop takes the RF in from the antenna, digitizes the RF, and sends it through the fiber. So what do? We grab the digitized RF, put it into our tools, and we recreate the RF spectrum as you would see from my previous slides, which allows us to see the RF data coming in. We don't see user plane, we don't do any of the tapping. There's no proprietary information in there, but it allows us to recreate the signal levels coming in. So what does that mean for you guys as PIM testers? It means when I look at the tool, not only am I seeing what the carrier sees, so I can see that there is no traffic getting in, or I can see that, hey, this antenna, the first of my 4 antennas in this one, why does it have a higher noise floor than all other antennas? Or why is 2 of my antennas have a higher noise floor than my 3rd and 4th antenna? We can see that by just plugging into a working station, not climbing the tower, so we're not up at the top, and we're using the system just like the carrier would. So just like an AT&T or T-Mobile would when they dial into their system and look for an RTWP number or look for PIM. Some of the carriers have algorithms they run that actually predict PIM. We can see that because we're running the same measurement. And it's done in a matter of seconds on a live site. So you see what they see. So what does that allow us to do? One, we're going to make the measurement from the bottom of the tower, as my picture shows up here on the left side, on the right side of the screen. We're going to do it on a working cell site. So as someone who has to go out there and fix it, the maintenance window becomes irrelevant because once we disconnect the site for about 30 seconds, put it back on air, we are able to view that site without any interruption to whatever service they may have, which means you can do your PIM mitigation during the day, during the night, weekdays, weekends. It doesn't matter. We're non-interference. We can see the presence of all 4 antennas at the same time. So we're going to see a lot of information without having to go to antenna 1, port 1, antenna 1, port 2, if it's a 4x4 MIMO, for example, or even a 2x2 MIMO. And it also allows us to look at multiple antennas at the same time if you choose to do that. So my AT&T example, I've got a band 14 and a band 17. Why not put them both up and I can compare the two if you want to. It's usually not how it works, but you're welcome to do that. So let's take a look at this. And this is an example of what it looks like on a single. This was an example from a JMA antenna that we're at. The antenna is kind of irrelevant, but the picture is a JMA antenna for those who are familiar with them. Has 8 ports, 4 ports for band 17, 4 ports for band 14. And we're able to plug into the fiber link coming down from the baseband unit. And you can see at the bottom here, I'll just focus on the one that says ONA 800. That's the tool we tend to sell more of. I actually have branches that are higher than the other ones. So, I mean, in about 5 seconds, you can look at it and go, okay, I know which 2 antennas I need to focus on, or which 2 antenna ports, I should say, to focus on. I can get up there and crank down with my my wrench to see if they just hopefully just a torque issue. I can take off the coax, move it around to see, is my interference following the antenna, or is it following an internal parts problem? Do I have a coax problem? Do I have an antenna port problem? Do I have a radio port problem? That can all be done by just looking at the screen and making modifications. Or do I have an external PIM problem, which of course is the piece we're going to talk about in a lot of time here. So a quick PIM testing versus PIM detection. And when we say PIM testing, this is traditional 2-port PIM testing. There are some stark differences and a lot of things that we all need to understand on this call. There are times when our method does not work, and that's the initial construction phase. So in this example here, and I'm going to jump back a slide, in order for us to see the RF coming through the fiber to make the measurement, the baseband unit has to be active. In order for the base unit to be active, we need to have a working cell site. So during the construction phase, you don't have a working cell site. You have the bits and pieces and parts of a cell site, but you don't have your backhaul. You may or may not have power yet. Traditional PIM testers, Kalis, Rosenberger, and Ritsu, absolutely, that's their shining moment there. They're very good at distance to PIM. They're very, well, I shouldn't say very good. They have the ability to do distance to PIM. We can argue the reality of that depending on where the PIM is located, on how accurate it is. And they're 1 port at a time. And they're starting to develop 2-tone or 2-port PIM testers, which do 2 tones out of 2 ports instead of 1 port. That's something that they're working on for one provider. And they're done at the antenna. I think you guys probably know this. If you've ever done PIM testing with them, you get it. You know, pull out the coax cable, put on a PIM rated load, test all of that, plug it into the antenna, run your PIM measurements on branch 1, then branch 2, branch 3, branch 4. With the fiber-based system, right off the bat, it does have to be a live signal. So we're coming in after the fact when the system's been built and completed and it's turned on and the provider goes, hey, we have a problem. RTWP is high. We have a PIM algorithm that some providers use. Hey, we need you to get out there and fix it. The stark differences physically, our unit, depending on which unit it is a small unit, about 5 to 7 pounds. This is a predecessor one, but it's a single unit that uses a fiber interface. So no high-powered amplifiers, no calibration. You just have this unit here. Obviously, power of some sort, AC or battery operated, will work. I assume you guys can still see my video, so that's why I showed it to you. Ours is meant to be plugged in at the base of the unit. And what does that mean? From a rooftop, it's fairly simplistic. You can plug in at the antenna by unplugging the fiber there, or you can go to the base unit cab, do it there. Or if you're doing a CRAN, if you've got systems that are like the small cell systems and you've got an antenna that's 5 miles away, before we get out there, before we go out there and plug into each port, why not test it from the ground, figure out, is it branch 1, 2, 3, 4, is it all 4? You can test from the ground level before pulling out the crane or climbing the tower. And again, we look at all 4 branches at the same time. And I should say up to 4 because some systems are 2x2 MIMO. And again, that's 4x4, it's 4 traces, but it can be from multiple radios if you're having a massive problem with mixing. That tends to be the service provider who runs that test, not so much in a contractor field. One thing I don't have on the slide, distance to PIM. Because this is a working cell site and cell sites breathe, they move their power up and down constantly. There is not a distance to PIM in a CPRI-based system. So that is one limitation if you look at the way these things are set up. So we can't tell you, hey, that's 40 feet away if it's in front of the system. That's one thing we just can't do that in a CPRI-based system. It's been attempted, it's being worked on. It is inaccurate enough that it has never been developed by any of us out there. And there's a few of us out here that do this for a living with CPRI-based PIM, and it doesn't work. So you're not going to see a distance to PIM, but there's some mitigation techniques around that we can talk about. And again, people who've done this, you'll understand what it is as we move forward. How does it look? So in your baseband unit, in your DU or RU, or RSU if you're dealing with some Ericsson cabinets. You're going to have a processing unit with multiple fibers coming out. The kits that we sell to Electro and to our customers come with a fiber tap. So a fiber tap is just like an RF splitter, but it uses fiber. You plug the antenna into port A, so you pull the fiber out of the baseband unit, plug it directly into port A of the fiber tap, and you plug a fiber from port B of the fiber tap into the baseband unit, and that allows us to steal a little bit of light out of the signal. The base station doesn't know any difference. It's back in service thinking it's doing what it's doing, and we're able to see everything that's happening coming into the antenna. Or we could see everything coming out of the baseband unit, but that's always perfect, so we don't look at that. Again, that's a service provider problem, not a PIM problem. And it's that simple. Once that tap is installed, you leave it there as long as you need it there to fix it. Could be half a day, could be 4 weeks. It doesn't really matter. It's a completely passive device. It's just a prism that steals light from port 1 and moves it into a monitor port, and you can plug in and unplug your test equipment as needed. So hopefully that makes sense. Fairly simple. Some of the advantages, right? We don't care about bands. In the traditional PIM testers, you've got your low band for your 700 and your 850. You got your high band for your PCS and your AWS. Since RF-Over-CPRI takes the RF from the radio does all of that. We just plug in and look at it. We call it baseband RF, which means if it's PCS, AWS, 600, 700, 850, it's all the same once it hits that CPRI fiber, and we can recreate it. So that the test set I pulled up, the one to show you, is the same test set regardless of technology, regardless of frequency, as long as it's CPRI. And I say that because some of the newer radios, we talk about C-band and all the new stuff coming, those are not CPRI fed radios. Those are a technology called eCPRI. eCPRI is a completely different technology, and this we don't touch the eCPRI technology right now, but to keep it clear, eCPRI runs at a much higher frequency, and PIM is not being seen as an issue yet because it's too new. So there isn't a 2-port PIM tester at those frequencies either. So it's not like it's a limitation of ours. There isn't a PIM solution for 3.5 yet. It's too new of a technology. It's not been deployed widely enough. It doesn't go that far relative to the 700. So it's not being developed yet until there's a need, right? You can read the rest of this, right? It's be able to do a lot of triage and testing before you pull out all of the cranes, the hoist, the whatevers, right? And it's a whole lot easier to not replace an antenna than it is to replace an antenna. And this is a quick way to do that, or to at least look at it to make a judgment call. All right, so that's that. Let's talk about examples. What does it look like? I think I'm running very well on time. I want to show you some examples that we did. This one was in Ohio, and this is a Nokia fed system. So what we have in the picture on the right side of your screen is a parapet wall on a rooftop with multiple signals up there. As you can see, all the coax in there. And I keep forgetting to take that little red squiggly out of there. That's the antenna on that side, and then the RRH is right behind the antenna, and of course that's fiber fed down into the building itself. So we have a customer here that was running the tool over here on the left side of my screen, which is a T-Bird 5800. We have both tools, the ONA and the 5800. They both have the same code. They both work the same way. We tend to sell more of the ONAs into the contractor space just because of other features it does, which I'll touch on that later. So we tapped it in here, and this is an example that the customer gave us where he actually recorded this on his screen and then made a small GIF so we could present it. This is what the cell site looks like in real time. Obviously, it's much faster in real life, not this little looped animation. This is what they were up against. So if you look at this, as the signal goes up to where you start to see it flatten out and curve with the slope on the left side, this is what we call a breathing pattern. This is realistic of what our base station really sees. As the base station can't see some of the mobiles it's trying to talk to, it increases its power because it assumes, hey, if I can't see you, then the odds are you can't hear me, or if I can't hear you, you can't hear me. So the base station's constantly driving up the power and dropping the power as calls come and go. And as the power rises, you'll notice that that signal gets relatively flat. Yes, it's sloped. Let me get the slope this way for you guys. But all of those little square waves, all those things happening have gone away. And again, this is a little deeper than we need to go, but those little square patterns at the low end, that's good. Those are phone calls. Those are data sessions. When your signal's flat, that means it's noise. We can't see it. So like I said, some providers have algorithms that talk about this, some don't. But this is what it looks like. So the nice thing in Ericsson and Nokia, the two big providers in the US, they have a way to turn up the power on the transmitter without affecting the mobiles and that, but it takes that breathing up and down away. We call it OCNS or AILG. Those are the acronyms: OCNS for Ericsson, AILG, excuse me, OCNS for Nokia, AILG for Ericsson. TJ will correct me if I got that wrong. I tend to get that one backwards. What does it do? It takes that first picture and it turns it into the bottom one and it holds it there. Now the bottom one is a picture, not a video, but in real life, that's what it would look like after turning up and down the radio, or excuse me, turning up the radio. The important thing for all of us, every color of graph, every color of bar in there is a different branch off the same antenna in this example. So I've got 4 branches coming off of this antenna. So it's a 4x4 MIMO. One of them is heavily affected, which is the green one. And then the other 3 are also affected, but not quite to the severity of the green one. So what I would do in this case is immediately start with the mitigation technique. So the first thing you do is, branch 4, we call it branch 8 in this example. The engineer had actually 2 2x2 MIMOs in it. He's using the second pair, 2 4x4 MIMOs, excuse me. I would go to that one and crank on it and see, does it drop with the other ones? That'll be the first thing of an internal PIM problem. I have some better examples for internal PIM moving forward, but this is this case. And then after that, go with some of the new PIM mitigation techniques, which is coming up in the next slide. One thing to show you here, this is my service provider slide. In this example, not only do we have a PIM problem on branch 8, we still have that problem, but you can see that on branch 7 and branch 6, the 2 in the middle, they're actually taking some traffic, which is a good thing. And all that, again, for the service provider, it says, hey, your PIM crew can go out there and fix it, and you're still getting your revenue from that site, which means it's on the air and they can get their alarms down. So again, you guys are doing the work for the most case, so we'll leave that there. And this is what we did in this example. Honestly, we got really lucky. We took the big rocks, that we like to call it. So they took these radios that are sitting up there, these antennas, and we were working with Conceal Fab at the time. I'm not here to promote Conceal Fab. They're a good company. They make phenomenal gear. There are a lot of PIM mitigation companies out there, 3M, Conceal Fab, a few of the other ones. We used a PIM foil, which is a super lightweight Mylar type blanket, but thicker. And we started just kind of covering the wall. And you can see, with the system still up in full power, we went from what we call the before picture to the after picture. And what does that tell us as a PIM crew? What does that tell us? Well, if I look at the screen, I had a power of X, and I'll show you my power on the next screen or so, and it dropped down to a very flat signal with a very little slope. Before picture is a much higher slope. And all 4 of my signals are flat on top, or relatively the same to each other. So that tells me, okay, I just figured out a major problem with my system here. So some stuff I don't have in the slides because it's being developed in conjunction with AT&T right now. Is there are some new PIM mitigation gear coming out, such as 4-inch foam to wrap the antenna, not these thin blankets, not the 20-pound copper infused blankets that we all have, but there's some new ones that actually absorb RF, whereas most of the PIM blankets and pads out there refract RF. So they actually push it off in another direction, which if you wrap an antenna, it just creates PIM. So PIM foam is coming out. Again, a lot of people are working on this. Again, I'm going to use Conceal Fab because we work with them a lot. They've got an entire wrap solution which goes around the base, the antenna, not the base station, the antenna. And you look at our tool and you go, okay, if I've wrapped this entire antenna, which takes about a minute to do, and I turn everything up, if I have a PIM problem, I have an internal problem. Because if I've killed all the RF from the outside and blocked it, and I still see problems, I'm going to have a very good indication that it's the coax, the cable, or the antenna itself. The way they've developed their blankets or their pads is they come off section by section. So you can take off the back section. All right, do I have PIM in the back? Now I know where it is. The reason we worked with them to create this is there is no distance to PIM, like I said. So isolating direction is quite simple. The tool is a monitor. It sees everything. Versus actually moving things around, running a tilt, changing your red. We can see all of that in real time. So that's where we are. And before I forget, on this slide, the picture on the far left is a small Android phone with our app on it. Every one of our systems has a remote viewing capability. So one of the biggest things that people say is, hey, if you plug your system at the base of a tower, or I'm going to use a rooftop for this example, and I'm up on the top of the rooftop, I've got to do all this, and then I'm going to go walk downstairs or have a crew of multiple people, obviously. So what we've developed, and this is not for this application, we've been doing this for years, is if there's an internet connection via in-house Wi-Fi, via hotspot on a phone, all our tools have a remote app that is completely free for use, runs on Apple, runs on Android, runs on Windows, does not run on Macs. That's the one thing we don't support. But if you have a tablet or a phone or a PC, you can have this tool running and you can see everything and control everything from the device. So you have your tool, I don't know, 50 feet away, and you've got this here. So you run your PIM thing, you get back from the antenna, you can see in your phone and you can see the changes that's happening in real time. We find that most people like to do this with 2 people or more because it makes it that much easier so you can not have to walk back and forth. But it's fully capable to view everything with not being in front of the test set. Now, the other option is you could have plugged the test set into the fiber coming out of here, but you have to be careful because we're a piece of metal and we have electronics and things can bounce off us too. So we tend to like people to plug these in fairly far away, roughly. But it's fiber. You can tap right here and you can put 100 feet of fiber onto the test set. It doesn't matter because it's from an RF point of view, it's a lossless technology. So for those who've done this stuff, I mean, the sky's the limit of where you put things, right? So, I'm not going to talk too much on this slide. Yes, sir. Yes, sir.
Can you go back to that slide? Can you just walk us through at a high level summary how long it would take you to, from understanding there's a problem to actually setting it up and doing some work on the roof? I mean, just roughly.
Sure. So in this example, what happens is you get an indication there's PIM from said provider. And I'll just be clear, this is an AT&T example, again, because a friend of ours did this for us. He got a notification that, hey, there's a PIM problem on site XYZ. So he went out there. You have to shut down the site. So you basically, you don't have to shut it down. You have to block the calls on the site. So when you pull the fiber, you don't drop it. That takes, for an AT&T engineer.
You mean on one sector though, right, Dan? You mean on one sector, not the entire site?
Yeah.
Okay.
Yeah. You block the one sector. Thank you. You plug in the fiber tap. That takes about a minute. We actually just scope and clean your fiber just to make sure nothing's dirty. You plug in the tap, you plug the system back in, and then you unblock that sector. So that process usually takes under 2 minutes if you're fast, usually under 5 minutes if you're not fast, because it's a single connection in and out of the tap per fiber. From that point, you calibrate our machine. So we have an auto config. I'll go to that in a couple slides. That takes about a minute on a Nokia site, takes about 3 minutes on an Ericsson site. It'll auto config to the parameters of that site. And then from there, oops, am I going the wrong way? I'm going the wrong way, aren't I? Of course, we're recording this. From there, the signal, the time to fix, it really depends on the area you have to cover, right? In this case, This one took us less than 5 minutes. We went down there, pulled it out, started just to unroll it and watch what happens in real time to figure out where the, is this affecting it, yes or no. This process takes time, but it's just like any other PIM hunting process. Setup of the tool is under 5 minutes to get to this level here. And then of course it's the PIM techniques, and that's whatever you guys have in your arsenal. If you have blankets, if you have this, if you're changing RET, if you're using like a PIM wand with a spec in, that's still doable, by the way. Some of the settings change in how you do the spec in, but you can still do a PIM wand and do the same excitement of the metal as you did with a 2-port PIM. Those are all the same. TJ, anything else you'd like to add?
No, that was it. I just was curious. And then setting up the remote screen and the remote control, that takes what, a couple of minutes as well?
At the most. You get a hotspot. That's usually the longest part. And then the unit itself has a little button that says remote, and it gives you a code. You put the code into the app on your phone, and that takes about 30 seconds. So this whole process to get here is quick. Again, the long part is obviously finding and fixing the PIM, but that doesn't change. We're just here to show you a different way of doing it. Right?
Hey, just out of curiosity, if there was multiple people on the roof that wanted to essentially do work to mitigate, can multiple people, would they have to stare at one phone, or can you do multiple connections?
That's funny. That's like you teed that up for me. Yeah, we allow up to 5 simultaneous connections anywhere. So what does that mean? Thanks, TJ. I forgot to do that. So the picture is the person with the phone. If you have a problem or you need help, you would call someone like myself or maybe the person in charge and go, hey, I'm seeing something weird. Give them the code. This is an internet-based remote control. I can be sitting in my house, which I am right now. You give me that code, I can see your screen in real time. I can control your screen, and I can come up with, hey, this is what I'm seeing. Now let's go to this measurement screen instead. It is a full remote control, not just localized, but it's, again, since it's using the internet, anyone can look at it if you give them the code. It's not Big Brother. You have to give them the access code. So, exactly. So I am going to skip this slide. Again, this is a service provider slide. I'll give it the 30 seconds it deserves. CommScope has developed a PIM calculator. There are times when you'll get a customer, and I'm going to pick on T-Mobile for a second, not that they're bad, but they're having some issues with the Sprint purchase. They'll come and say, hey, we have this high RTWP problem. We have PIM, I need you to fix it. And they'll tell you, hey, it's this sector, this frequency, and this is where we're seeing it. CommScope actually makes a software where you can plug in, hey, okay, so if you're telling me the PIM is on this frequency here, and this is a horrible thing, AWS, right? So this is an example. Again, it's not T-Mobile, but I'm using as an example. You say you have PIM here. Well, if I plug in my calculator, you can put a pretty educated guess to say, yeah, you have PIM, or no, you don't have PIM, because based on the combination at your site, that's not possible. So this is a calculator for the people who want to do a little bit of pre-work to see, yeah, this is the most likely scenario of PIM I'm going to have. We don't charge for it. They don't charge for it. We have no affiliation with them, but it's a good calculator. We use it a lot when we get that call of, hey, we're seeing something weird on the site. First thing we'll do is plug it in and go, okay, that is a potential for PIM. Or better case, I'm over here at block A. No, you don't have PIM. You've got something interfering with you. Now we can run the same tool, but it's a different methodology of fixing it, right? You're not going to go out there and start covering the antenna. You're going to start looking for potential interferers that are electronically driven, cordless microphones, things that actually generate power, repeaters, stuff that is not, you can't just fix them, right? You got to shut them off. So, and the reason we say that is this one was a T-Mobile example. Just to show you guys kind of what it looks like. And again, this is a very good service provider slide. My counterpart, Steve, on the East Coast, went out to a T-Mobile site where they said, we have a high RTWP problem on one branch of our 2x2 MIMO. I'll use the top one because it's prettier in colors for this example with the screenshot we took. The red one showed normal, whatever that is. And by the way, RTWP is a channel power measurement. It takes that signal and it averages it to a single number, and that number is something like negative negative 90 or negative 95 or negative 115 dBm. The blue one, excuse me, I had that backwards. The blue one said normal because they quantified, or they added up all the power that they saw at the radio. This is the, I think this is an Ericsson system at the time. And the red one was higher. So they saw the two numbers and they said, we have an RTWP problem, something's weird. So they brought us out there. Steve went out there and he plugged in and saw this. And he goes, you don't have an RTWP problem. You have a bad radio, period. He also brought the second tool, the ONA 800, so we can see both, because once he saw that, he realized this is a good training slide. So what they thought was purely an interference problem and a PIM problem was actually a bad radio. So what happened is they swapped the coax and it moved, or it didn't move, excuse me, stayed with the radio. They went back, they swapped out the radio, and this is what happened. So the radio now is transmitting correctly, and the two branches are right on top of each other, and they're fairly flat. You could argue that there's not enough PIM here to warrant fixing. And again, the before picture is actually had a radio that had we don't know if it was a bad filter, we don't know what it was, but clearly it was going about 3 megahertz wide and just dropped off to the face of the earth. That's not something that happens. You know, they know how wide their signal is because they've paid for that. And these two should always be a mirror image of each other, or the same, minus the height, right? So the nice thing is from this one is, you know, the crew went out there, they were able to fix it without having to spend hours of troubleshooting, just being able to see it in about 10 minutes, right? Some examples, and again, I've got a mix of old screens and new screens, so bear with me on this one. This is an example of on-pole, or what I would say internal PIM. So in this case, I have two branches. One branch is flat. The second branch on the top here is not flat. And just to keep it clear, we had changed some of the graphs around. So this one is not three radios or three antennas. It's actually a max and min marker to look for severity. It's two radios, where we can see that one of them is nice and flat. The other one has a very bad slope. That is a very strong indicator that this is a radio or a coax or a port problem, not an external problem. Because external PIM does not care what antenna you're on, it's going to affect them all. Some more than others based on the phase of the antenna or the azimuth, but it's never only one unless it's an internal problem, right? This is a very similar example, but in the newer software. So this one you can see I've separated them out left and right, put a little history on it. But you can see here I've got a flat one and I've got a not so flat one. I personally don't use this screen very much unless I'm building graphs, because the history speaks volumes, especially if it's breathing. But we've moved into a newer screen, right? Some examples of isolating a single antenna, bringing it into 4 antennas, and the newer screens is, instead of trying to look at all 4 antennas and figure out which one here in the middle is the high one, why not put them all 4 on the same screen? You don't even have to think. You just turn it on and, hey, guess what? The red one is higher than the other 3, and I dulled out the other colors on purpose. I've got a question mark there on that antenna. And lastly, per some AT&T requirements, we have added metrics to this, which help for everybody, but we specifically did this for everyone working with AT&T systems, is we've quantified the channel power. We call it RSSI. T-Mo calls it RTWP. This is the CPRI version of that. Again, I don't honestly care about the numbers, but I can tell you neg 93, neg 94, neg 94, close. Why is this one neg 75? I clearly have a problem with this one. And again, for people who don't like to look at graphs, because a lot of times we've always dealt with numbers, we put them in numbers. We've added slope values to see the severity of the tilt that may or may not be happening. And I can tell you from an AT&T standpoint, they're focusing on numbers, not slope. But slope is powerful, and some people do focus on it. So we've kept them both in. But now we're looking at numbers to keep this as similar to the traditional PIM testers as we have. So I've done a lot of this, but this is the setup. I've got about 5 more minutes, and then we'll open this up for any questions. Thank you, Alan. That's perfect. So this is the setup we talked about. In a traditional environment, you're going to have the baseband unit, which is a BBU and Nokia, a DUS and Ericsson. You're going to plug it into the B port. You're going to take a fiber. You're going to take the RRH, Nokia, RRU, Ericsson. You're going to plug it into the A port for antenna. And then that's going to span out to us, right? So it's all done with simple fiber and some SFPs. And from there, I'll just get back this one. It's going to automatically configure itself. It's going to, well, not automatically, you got to hit the auto configure button, I guess. And it will display the screen so you can then do your job, right? And there's various mobs on how to. But what is the tool that we're offering through Electro? It's one of two. This is the first one. This is the One Advisor. The reason we tend to work with this one more is it does RF-Over-CPRI. It does PIM analysis, everything we talked about, but it also does traditional cable sweeps. So distance default, VISWAR, return loss. It has an OTDR on the back if you choose to have that for OTDR testing. You can plug scopes into it. If you're doing a lot of interference testing, so if you're one of the contractors that not only does PIM and maybe installation and kind of soup to nuts build, but you're doing RF testing, it can also be a spectrum analyzer. In fact, it's the same hardware that does PIM and spectrum analysis. So it can actually do real RF interference with antennas and all of that. Highly configurable. And so what happens is we have base packages we put into our partners, and then we can configure those with our partners up and down with license that you may need depending on what you're doing. So this is our very flexible kind of contractor-based system. We also do the 5800. This is not an RF box. That's the big difference. It will do an OTDR, but it will not do the cable antenna analysis, so no site master type tools. But it will do everything else minus the spectrum analysis, right? It has the same code for RF-Over-CPRI. The only big difference is it has a black or a white background screen, and the ONA uses the white screen, which doesn't look as good on a presentation, these white screens, but outside, the white actually becomes brighter and is daylight viewable. The black screen is for indoor use, the white screen is for outdoor use. We tend to do more outdoor use in this environment. That's why you see a lot of the white background. And a lot of these T-Birds are out of the market, and Electro has tons of these out there. So these can be outfitted with a software option to do everything we've talked about. Yeah, and this is just a quick look at the similar and capabilities and differences between the two. The biggest difference here, spectrum analysis and cable sweeps and interference hunting. This unit is not designed to do any RF. But again, that's a slightly different topic, same hardware, right? With that said, that's the end of my presentation. I know it was fast. I apologize for that, but wanted to make sure we get time for any questions. And we've got about 10 minutes left.
Yeah. Dan, thank you so much for that presentation. It was really great.
Okay. TJ, anything you'd like to add, or anyone have any questions?
Yeah, so Dan, what service provider-wise, do they use this? Do they approve of it? What's the outlook on that?
So let's start with the big one, AT&T. This is absolutely approved in AT&T. In fact, as we just finished the training course, and we're going to start offering training down in Dallas, Texas on this in January. We just went through the final phase of that in conjunction with Conceal Fab, myself, and AT&T. They have approved it for all PIM moving forward. Verizon it's approved as a system inside of Verizon for RF-Over-CPRI, and same thing in T-Mobile. They're fully approved. The difference between AT&T, Verizon, and T-Mobile, we'll start with T-Mobile there. AT&T, 100% yes. And in a lot of cases, if you're the prime on AT&T, for those who've worked with AT&T know what that means, it's going to be mandatory with screenshots. You'll see that coming quickly. T-Mobile doesn't care how you fix PIM. They just want it fixed. So it is approved because they've said, we are farming this out to the PIM crews. They are going to fix it however they want to do it. And so, yes, it's approved because it's whatever the contractor wants to do. Verizon is region by region. So I don't have a global yes or no on Verizon. But the regions I cover, the West region said, sure, as long as it's fixed, very similar to T-Mobile. We don't care. We don't have time to do this. We're working on C-band and all the other stuff. We just need our stuff to work. So in the West it is. TJ, you probably know the rest of Verizon better than I do, actually.
Yeah, they're fine with it. Like you said, they just want the PIM fixed. But I had another question on that too. So we're talking about PIM the whole time, but do they use it for anything else, like interference hunting, or to verify what's going on in a sector if they have an issue?
Yeah. So one thing I completely glossed over, and I appreciate that, is because we're grabbing, let me just get to a screenshot so you can see it. Sorry about this. Because we're grabbing all of the RF that comes in from the antenna itself, I focused on PIM, i.e. this example you guys see here. But if there was a narrow band interferer, if there was something going on that would cause part of the signal to raise, not that one example I showed from T-Mobile with a bad radio, but with massive spikes in here, you can come back and say, you've got potentially a PIM problem, see all this stuff, see how the whole thing's risen, blah, blah, blah. But you also have X, Y, and Z. You have some massive external problems that show up as interference. And I really wish I had a slide on this. And what they look like is spikes, not wide noise like you see here, but narrow needle point spikes, almost like a CW tone again, that will show up in 1, 2, 3, 4, 5 spots across that signal you see on the screen. Those are classic external interference. And when I mean external interference, that could be from that other example I had here. I apologize about jumping over. In this one, this big air conditioner on the roof, right? It may have a PIM problem because it's metal and probably rusted, but it also is powered by DC. So if you have a bad DC power supply in here, like fluorescent lights in a lot of these older buildings, or anything that uses DC power, if that goes bad, it creates that spike we just talked about. It doesn't create a wide noise that covers the whole thing and slopes up and down. It creates these narrow spikes that pop around. That needs to be characterized. It can be seen the same way we see it here, and you can go back and say, yeah, we fixed this, but here's all the stuff you're not paying us to fix, right? What do you want to do about it? And that becomes the ability for this tool to look for and characterize any external interference, non-PIM related, as well as PIM. It actually does both. That's a great point, TJ. Yeah. I think the only question we had, and Alan answered it, is this deck available? Alan, I apologize. I was supposed to give you this deck last night. I didn't do that. I totally forgot to give that to you last night, and I realized that this morning. So I will get this to you as soon as we finish this, and you can, it'll be PDF, so the little video won't work, but and you can forward that on. That's 100% on me.
Absolutely. This, like I mentioned previously, this recording will be distributed. It will also contain the presentation as well.
Yeah, and the floor is open if there's any questions or comments.
We love what you've done in the room, Dan. I think I speak for everyone here.
Nice, yeah. Most of that.
Hey, Dan, I have a serious question though. I know the service providers like RF-Over-CPRI for the most part because it gives them some intelligence. But would you say, and I'm being sincere here, would you say that the biggest benefit to it is that when you're trying to fix PIM with a regular two-tone PIM tester, you're kind of guessing at things because you don't know what the receiver is actually seeing. With this, would you say the biggest benefit is that you actually know that you fixed the PIM problem because you could see it real time on the unit?
Yeah, that's AT&T's take on it right there. Is when you go out, two things. One, when you go out with the traditional PIM tester, it takes days in a lot of cases to set it up, make sure it's calibrated. Port 1, find all the PIM problems, cover them. Port 2, 3, 4. With ours, one-time setup, we already went through all that. So it's quicker, but at the same time, when we see that number on that screen drop, it is the exact measurement that AT&T is making for their internal tools that we talked about earlier. So when you do fix something, or when you see, hey, I've got a 7 dB drop on this, it is a 7 dB drop in their system as well, as long as they make the measurement while it's covered or fixed, of course. When you do it with a traditional PIM tester, you're going to find problems, and you're going to get the PIM wand out, and you're going to find things that just light up like a Christmas tree, but they may not actually be bouncing back into the receiver. And that's the reason why, very specifically, AT&T's looking at this, is their problem is massive, and they want to make sure when you fix it, it is seen at the receiver to make sure it's actually fixed. I don't know how to say it any better than that, other than you're not fighting problems that don't exist. They're problems, but they're not affecting the receiver itself, right? I don't know if
so real-time confirmation that you fixed the problem is probably the best way to sum it up.
Yeah, it's a good way to put it.
Awesome.
It looks like we don't have any additional questions.
Okay.
Yeah,
So
let me grab this screen from you. 1 second here. Well, thank you everybody for attending the webinar today. Again, I do want to thank Dan Smedja, TJ Ford for bringing this presentation to life. If you do have any questions, please call us at 800-553-2255 or electron.com, and we will gladly answer any questions that you have. And again, from on behalf of VIAVI Solutions and Electron, thank you so much for attending.
Yeah, thanks everybody. Thank you.
Bye-bye, everybody.